Well, our dialogue continues about sum and difference formulas, and in this video we are going to discuss how we can use sum and difference formulas to verify some trig identities. Now, you've already seen some verification problems before, and now we're going to use the sum and difference formulas as a tool that will allow us to verify some trig identities that maybe we couldn't before. So let's go ahead and jump in.
Okay, so I've got a couple of examples here. I've got actually three examples that we're going to look at together. But for each of these equations, we are going to use a sum or difference formula to show that the identity is true. Okay, so let's start with this equation on the left. Here I have the sign of the quantity x plus pi over 2 is equal to the cosine of x. So we want to think about this in terms of a sign of a sum, okay? And so then we'll use our sum formula for sine and expand this left-hand side. So that would be the sine of x times the cosine of pi over 2 plus the cosine of x times the sine of pi over 2. And we're going to just leave that right-hand side alone and call it still the cosine of x. All right. So now if I'm looking at that left-hand side, I recognize that while I can't evaluate sine of x or cosine of x because they're variable expressions, I can evaluate cosine and sine of pi over 2. So we can replace this cosine of pi over 2 with 0 and the sine of pi over 2 with 1. And then if I'm looking at what I have a product of sine of x times 0. Well, that will just go away. And I'm going to add that to the product of cosine of x times 1, which will just become cosine of x. And I have shown that these expressions on the left hand and the right hand side are truly equal to each other. Now, the example on the right here, I don't see a sum or difference going on as it's written. But I can take this left-hand side and break it apart because I can say that 2x is actually the same as x plus x. And then I can use my tangent sum formula and expand that. Okay, so I'll use this tangent sum formula, which means I'm going to use the top signs, S-I-G-N-S, and I can say, well, if I am expanding tangent of x plus x, well, that's tangent of x plus tangent of x divided by 1 minus tangent of x times tangent of x. All right, well, now let's combine like terms. Tangent of x plus tangent of x, well, that's 2 tangent of x, right? And tangent of x times tangent of x is tangent squared of x. So I'm exactly where I want to be. All right, and then our last, I saved the best for last. The last example is a little bit ugly, and we're going to need to just be very careful with our signs and our expansions, okay? Now, I've got a product of the cosine of a sum times the cosine of a difference. So I'm going to take and expand this cosine of a sum using my sum formula, and I'm going to expand this cosine of a difference using my cosine of a difference formula. And when I do that, I get something really long and ugly because cosine of alpha plus beta is cosine alpha, cosine beta minus sine of alpha, sine of beta. And cosine of alpha minus beta is cosine alpha, cosine beta plus sine of alpha, sine of beta. All right, so it's ugly, but we are going to see what we can do and make it look like what we have on the right-hand side. Well, notice I have really an a minus b times a plus b situation. So I can multiply these together and get a squared minus b squared. So I will end up with cosine alpha times cosine alpha, cosine beta times cosine beta, minus sine of alpha, sine of alpha, sine of beta, sine of beta. So we'll end up with cosine squared of alpha, cosine squared of beta, minus sine squared alpha, sine squared beta. And we want that to end up looking like cosine squared of beta minus sine squared of alpha. Okay, so now if I know that's what I want it to look like, notice that I have a cosine squared of beta here and a sine squared of alpha here. So I'm going to think about what can I do with this cosine squared of alpha to make it look a little bit different, and the sine squared of beta. And when I'm thinking about sine squared and cosine squared of anything, I am going to be thinking about Pythagorean identities. So I'm going to rewrite this cosine squared of alpha as 1 minus sine squared of alpha. And I'm going to rewrite this sine squared of beta as 1 minus cosine squared of beta. Okay, so now this doesn't look like it really did me any good, but let's go ahead and distribute through this cosine squared of beta to both of these terms and this sine squared of alpha to both of these terms and see what happens. Okay, so this will end up being cosine squared of beta minus sine squared of alpha cosine squared of beta, and then I'll subtract sine squared of alpha, and then I'll have plus sine squared of alpha cosine squared of beta. Okay, so what does that all look like? Okay, doesn't look like I got very far here, but oh, if I look closely, I notice I have sine squared alpha cosine squared of beta here and sine squared alpha cosine squared of beta here. One is positive and the other is negative. So those two pieces negate each other, and I'm left with just cosine squared of beta minus sine squared of alpha, which is exactly what I want. So this is just kind of marrying two concepts that we've already been using and putting them together, using them together to solve some problems. In the next video, we will talk about using the sum and difference formulas to evaluate exact values of sums and differences given specific conditions, and that's where we'll pick up next time. See you then.